Hello everyone. In this video, I'm going to go over example 3.8 from the book Heat and Mass Transfer by Cengel, Cengel, and pretty long statement of the problem here. So what I will do is I'll summarize it for you. So basically the problem is we have a cast iron pipe. The length is going to be 1 unit, and it has a wool insulation around it, and a steam flowing inside of the pipe, and it is at 320-degree temperature, and so as a result of that, the mechanism is when you have such a high heat is going, and the ambient temperature happen to be 5 degrees centigrade, so it is going to lose heat. So what he wants to know, what is the rate of heat transfer in a situation like this. So the information he has given is the ambient temperature, inside temperature, convection heat transfer inside, and convection heat transfer coefficient outside. And then also here, because the cast iron pipe, then there is the thermal conductivity of a cast iron is 80 and watts per meter square, and also thermal conductivity of wool is 0.05. Naturally, cast iron, it is a very good heat transferring material, and wool is highly insulation material. The heat transfer is very little. So the question is determine the rate of heat loss per unit length. So he wants to know at the unit length. So that is, what is the rate of heat loss? That is Q dot. And temperature drop across the pipe. The second part of the problem is temperature drop across the pipe. That means from inside just across the pipe, the thickness of the pipe. And then he also wants to know temperature drop across the thin insulation, across the insulation from here all the way, how much temperature is dropping. So when you have a problem where there are different materials are involved, for example, here's inside is a steam carrying, inside is the steam is flowing through, and that has a convection heat transfer. And then you have the cast iron pump that has a conduction taking place. Then you have a insulation, there is another conduction taking place, and from the surface of this to the ambient, there's another convection type of heat transfer. So what you do is, first thing you do is you develop a thermal circuitry, and starting from the inside T1, and then first thing is convective heat transfer between the steam and the pipe idea of the surface, there is convection, and then that is from there the heat is being transferred to across the thickness of the pipe, that is R1 thermal resistance of the cylinder, and then you have from there to the insulation material, so R insulation, and then from there to the convection. So this is the first step. And what I have done here is I took a cross-section view of that pipe, and so R1 is the diameter, and it was all the dimensions are given in centimeters and plus also in diameters. So I converted them into radius. So R1 is 0.25 meters, from centimeter to converted to meters, and then so also R2 and also R3. R3 is basically from the diameter, the radius of this one all the way to the surface of it. Then so I have the thermal circuitry, and to solve the problems, what I'm going to do is take some of the important information, transfer onto my page, and I think that way you have a pretty good idea of how the how the calculations are involved, and you have some all pertinent information with you, and then you can proceed with the problem solving technique. Okay, so given that, first all we have to do is find out R total, that means total resistance of the thermal resistance of the circuitry. So R total is given by, I'm trying to write as big as possible here, R total, total, just 1 second. My pen is acting up here. R total. Okay, let me switch the pen here. That's much better. R total is equal to R I convection, which is inside of the inside surface, R1, which is the cylinder, and R2, put on R cylinder maybe here, yeah, R insulation, plus R convection 2, that means from outside to the ambient air, convection 2. So we know there are two conductions taking place, and two convection heat transfer. Okay, all right. So that gives you, because it is series, if it is a parallel circuit, it is a different story. So now what is the formula for thermal resistance convection, thermal resistance cylinder, conduction, and so on and so forth? Let me write the formula for that. That is 1 HI, that is inside, and A1 for the thermal resistance for the convection heat transfer, and for the conduction heat transfer, logarithm R2 over R1, that's inside radius and outside radius, divided by, and 2 pi length of the pipe L and K1, that is for the cast iron. So that is for this cylinder. And let's do the insulation also. Log, which is also conduction, that means R3 over R2. R3 is the OD of the insulation material, radius of the insulation material, and that is also divided by 2 pi L K insulation. And the last one is convection heat transfer, very similar to this one, where H convection out second. This is the second type of convection: inside convection, outside convection, and then cross section area of the not cross section, is the surface area of the insulation pipe, insulation sleeve that is going on. So we have the formula is written, and the next step for us to do is figure out. So you notice we have inside surface area, and also we need outside surface area. So the formula for the inside surface area, A1, let's try to write it small because I need a lot more paper here, and A1 is 2 pi R1 L. So R1 is given, all the information is, length is only 1 unit, so if you plug those values, you come up with a 2 pi 0.025 times 1, and that value of A1 turns out to be 0.157 meters squared. And let's do the same thing for A3. Remember here, A3 we need to find out. So same formula, 2 pi R3 times L. So 2 pi R3 given to be 0.0575, 0.0575. I'll put in a parenthesis here, times length is 1 meter, and if you crunch that value, and it comes out to be 0.361 meter square. So going back to this, we have H1, and now we figured out A1. I'm going to just circle A1 here, and then we have A3 here, circle that one out. H1 is known, and H2 is also known, and K1 is, we have the value for the K1, and K2 is also given. So it's just matter of plugging into the formula. If I go and substitute those values, 1 over 60 watts per meter square Kelvin times A1 is, we just found out the value, 0.157 meter square. So there's one, and the second, I think, let me plus this log R2 is 0.275, R1 is 0.025, I'm sorry, 0.275, 0.025, that is divided by 2 pi, length is 1 meter, K1 is given, K1 is 80 watts meter Kelvin. So similar way, logarithm of R3 over R2, R3 over R2, R3 is 0.0575 divided by 0.275 divided by 2 pi. 2 pi, L is 1 meter, K insulation is given to be 0.05 watts meter Kelvin. So the last one is convection heat transfer, this part of it, and I think here one plus, another plus, and third plus. It is getting crowded here, but we'll do our best here. 1, convection heat transfer is given to be H2 is 18 watts, and surface watts meter square Kelvin, and times A3, we just found out A3 here, A3.361 meter square. Okay, sorry for writing so small. I'm trying to capture everything in one place. So now by simplifying it, this value comes up to be 2.61 degree Kelvin, degree centigrade per watts, and the thermal resistance of the cast iron pipe comes up to be 0.0002 centimeters per same units, and the now insulation thermal resistance comes to be 2.35 and degree centigrade per watts, and the last is convection heat transfer for outside ambient is comes up to be 0.154 degree centigrade per watts. If you add them up, the total value of this would be the R total. I think I got this one wrong. It should be 0.160, not 0.1. Let me do it. 0.160. Okay, so add them all up together, it comes up to 2.61. Okay, so 2.61 degree centigrade per 2.61 degree centigrade per watt. This is the R total. And so we have the information what we needed now. We want to know, the question is asking steady state heat loss. Basically, it's asking, this has to be a steady state for this one. So Q dot is equal to T infinity minus 1, T infinity 1 minus T infinity 2. That means inside temperature to the outside temperature divided by R total. That is a formula. If you plug those values, 320 minus 5 divided by 2.61, and then here is degree centigrade, and this one unit for this one in degree centigrade watt, and if you crunch these values, it comes to be like a 121 watts. This is a heat transfer, Q dot, the value of Q dot. Yeah. So we solved one problem. Now the second problem is, there are two parts to it. He wants to know delta T across pipe. And very simple. All you have to do is heat transfer, the one you found out, times the resistance circuitry of the pipe. That we know that value will come up to be this. So you multiply with that. R pipe. So 121 watts times R pipe is 0.0002 degrees centigrade per watt, and if you watts gets again cancelled, and you come up with a temperature of 0.2. If you really think about it, there is very little temperature difference inside and outside, almost negligible, 0.02 degrees centigrade. So that means whatever the heat it is transferring, whatever the heat inside is also outside. But basically, that's what it's telling us. But next question is, this is A, and B is delta T across insulation. That is also same formula, Q dot R insulation. R insulation we found out to be this value. So 121 watts times our insulation is 2.35 degrees centigrade per watt, and if you crunch that number, it comes up to be 284 degrees centigrade. So basically, inside temperature is in a way, what is most of the heat is the resistance of the whole across is most of the heat transfer is the benefit of the reducing the heat transfer is coming from the insulation material on the outside. The insulation is what causing it. So you could say, in a way, that where the temperature between the inner and outer wall surface insulation difference is 284. So from inner wall to the outer wall, the temperature difference is 284. And in a situation like this, the resistance to heat flow in an insulated pipe, this is insulated pipe, is particularly due to the insulation itself. The insulation material is what resisting the heat flow from inside to outside. So those are the benefits of the heat insulation. That completes the problem. I hope you understood this, and we'll work on another video for the second problem on the same subject.